Hello, everyone. You know when you're scrolling through Instagram and you tap on a filter, have you ever stopped to think what's really going on behind the scenes? Well, today we're going to pull back that curtain. We're diving deep into something you use every single day, the magic of color image processing. I mean, seriously, think about it for a second. How does your phone know how to make a sunset photo look so dramatic? And on a more serious note, how does a self-driving car, something many of you might work on one day, know the difference between a red light and a green one? It feels like magic, doesn't it? But trust me, it's not magic. It's just really cool science.
So that's exactly what we're here to do today. We're going to learn the language of color, how to teach a computer to see the world just like we do. We'll figure out how we take what our eyes see and turn it into data a machine can actually understand and use.
Okay, first things first. To even begin, a computer needs a set of rules for color, a system. We call these color models. Now, the easiest way to think about this, imagine a painter's palette. These color models are like the set of primary paints a computer gets to work with. Its digital paint box, if you will.
And right away, we hit a super important point. Computers and humans, we see color in totally different ways. A machine, it thinks in terms of hardware, of mixing light. That gives us the RGB model. But us, we think more intuitively, right? We talk about a color's shade, how pure it is, how bright it is. And that's exactly what the HSI model is based on.
So let's start with the computer's language, RGB. It stands for red, green, and blue. Literally every single pixel on your phone screen or your laptop is made of tiny red, green, and blue lights. The analogy here is perfect. Think of a stage lighting person. They can mix red, green, and blue spotlights to create any color they want. And if they turn all three on full blast, boom, you get pure white light. This is the language of our screens, our cameras, our video games.
But now, think about how we talk. If I asked you to describe a beautiful red sari, you wouldn't say, oh, it's 255 red, 100 green, 50 blue. No way. You'd say it's a deep, vibrant red. See? That's the HSI model. H is for hue, that's the pure color, the red part. S is for saturation, that's the vibrant part. Is it a rich, deep red or a faded, washed-out pink? And I is for intensity, which is just how bright it is. This is so powerful because it separates color from brightness, just like our brains do. And there's one more key player, especially for anyone who loves watching videos online, the YUV model. This one is all about being efficient. It does something really clever. It separates the brightness information, we call that Y or luma, from the actual color information, the U and V or chroma. Why? Because our eyes are way more sensitive to changes in brightness than in color. So you can squeeze down the color data to save bandwidth, and we barely notice. It's like sending a high-quality black and white movie and then adding the color info separately. This is the secret sauce behind why your Hotstar or Netflix stream looks so good even on a slow connection.
All right, so let's put it all together. RGB, that's the king for anything you see on a screen, photos, games, your monitor. YUV, that's the hard worker behind the scenes, making sure your video streaming is smooth. And HSI, that's the smart one, the one we use for complex analysis, like teaching a computer to recognize things. Simple, right? Each one has its job.
Okay, so quick question to lock this in. Which of these color models is specifically designed to think like a human by separating a color's basic shade from how bright it is?
So, we've learned the different languages of color. Great. Now, let's learn how to actually speak them. We're moving on to transformations. Think of these as our digital paintbrushes and filters. This is where we get to manipulate the colors, and it's the real magic behind every single photo edit or Instagram filter you've ever used.
Let's start with a really cool and simple one, color complements. If you've ever seen an old film negative, you know exactly what this is. We're basically flipping every color to its exact opposite on the color wheel. So red becomes cyan, blue becomes yellow, you get the idea. Now, besides looking pretty cool and artistic, this is actually super useful for enhancing details that might be hiding in the dark, shadowy parts of a photo.
Okay, time for some Bollywood or Hollywood magic. Let's talk about color slicing. This is the secret behind every green screen effect. So how does it work? Well, first, we switch the image to our good friend, the HSI model. Why? Because it's so much easier to tell the computer, find this specific shade of green in HSI. Next, we define that exact shade. We're telling the computer, select every single pixel that falls into this narrow slice of green. Then, the computer highlights all those pixels. And for the final step, we just replace that entire selected slice with whatever background we want. A superhero scene, a news studio, anything.
And of course, we have the tools you've probably played with on your own phone. Things like brightness and contrast, pretty straightforward, right? Then there's something called gamma correction, which is like a more advanced way to control the balance between the dark shadows and the bright highlights. And color balance is a lifesaver. You know when you take a photo indoors and everything looks kind of yellow? Color balance lets you fix that by adjusting the overall red, green, and blue tones to make it look natural again.
All right, another quick check for you. If you were directing a big movie and needed to put your actors on a different planet, which transformation technique would you tell your VFX team to use?
Now, before we get to the really advanced stuff, like teaching a computer to identify objects, we have to do a little prep work. We need to clean up the image first. So think of this next part as adding the finishing touches, preparing our digital canvas by smoothing and sharpening.
So we have two techniques here that are basically opposites. First, there's smoothing. You can just think of it as a very specific kind of blurring. Its job is to reduce any unwanted noise, you know, those grainy little specks you sometimes see in photos, to make the image look cleaner. And then we have sharpening, which does, well, exactly what it sounds like. It makes the edges and fine details pop, making the image look crisp and clear. We use special math-based filters to do this, like a Gaussian filter to smooth or a Laplacian filter to sharpen.
Okay, and here is a fantastic pro tip that shows you just how useful that HSI model is. You could try to sharpen an image by applying a filter to the red, green, and blue parts separately, but you often get these weird, unnatural colors along the edges. The much smarter way? Convert the image to HSI and apply your sharpening filter only to the intensity channel, the eye. This way you get a beautifully sharp image, but the original colors stay perfectly untouched. It's a much cleaner approach.
So let's make this practical. You're working on a project, and you need to sharpen a photo, but it's absolutely crucial that the colors do not change at all. Which single component of the HSI model are you going to apply your filter to?
All right, this is it, the grand finale. We're going to put everything we've just learned together. We're now ready to talk about the final masterpiece, color segmentation. This is how we actually teach a machine to see and separate different objects in an image, all based on their color.
So, let's set up the challenge. Imagine you're programming a robot for a farm. Its job is to look at a big pile of fruit and pick out only the perfectly ripe strawberries. How on earth do you teach a computer to do that? How does it know which ones are the right ones? This is the exact kind of problem that color segmentation is built to solve.
And the solution, once again, lies in our HSI model. Here's the plan. First, we use the hue, or H component. We tell the machine, hey, just isolate everything in this image that has a red hue. Okay, so now we have the strawberries, but maybe also some red cherries. So next we use the saturation, or S component. We add another rule. Now, from that red group, only keep the pixels that are highly saturated, the ones with a rich, deep color. And just like that, we filter out any unripe, pale strawberries. And the result? By combining these rules, the computer can perfectly identify only the ripe strawberries.
So this brings us to the most important question of all. Why is the HSI model so much better for a task like this than the basic RGB model? The answer is everything we've been talking about. It's because HSI separates the color information from the brightness information. A strawberry can be in bright sunlight or in a shadow, and its brightness will change, but its redness, its hue, and saturation will stay the same. For a computer, being able to understand that difference is a complete game changer.
So, let's do a super quick recap of the Digital Artist Toolkit we've built today. We started with our color models, the basic languages like RGB and HSI. Then we learned about transformations, our filters for editing. We covered smoothing and sharpening, the tools for cleaning up an image. And we put it all together with color segmentation, the technique that lets us teach machines to see.
I want to leave you with this final thought. Everything we talked about today, this isn't just theory for your next exam. Understanding color processing is understanding a fundamental language that is powering our future. It's inside the AI that helps doctors find diseases in medical images. It is absolutely critical for the self-driving cars that need to see traffic lights. And it will be the foundation of the augmented and virtual reality worlds that you, all of you, will one day build. So please master this material, because when you do, you're not just learning a subject, you're learning how to create the future.